welcome to the third part of the basic fundamentals of transformers. We already covered the two parts, and this is the third and the final part. We are going to cover first the equivalent circuit. Let us see the practical transformer equivalent circuit excluding the no load current. So we will not take the no load current in the equivalent circuit, and let us see how it is. So the primary part of the equivalent circuit include the resistance and the reactance R1 X1, and the secondary part represent the resistance R2 and X2. These representation are corresponding to the copper loss, which is represented by the resistance present in the primary network R1 and the resistance of the secondary network R2. The leakage reactance X1 and the leakage reactance X2 represent the leakage flux in the transformer. We know that the supply voltage is V1 to the primary network, where the induced EMF E1 and E2 of the primary and the secondary are represented by two wires, where the voltage across the wire is E1 and E2. The voltage V2 is across the load. We do not have the shunt parameters here, which will represent the no load current and the power loss due to the core. However, when we include the no load current, we are having one shunt parameter branch included in the equivalent circuit of the transformer, and hence the primary current I1 is the summation of the no load current I0 plus the load component of the current I2 dash, which we have seen in the previous lecture. So the shunt parameters include the R0 and X0 representing the core losses given by R0 and the flux which is produced in the core by X0. If I0 is the no load component of the current, then that is distributed in the core loss component of the current as IW, and I mu represent the magnetizing current. So this equivalent circuit is used when we need to determine the core loss parameters and the primary and the secondary parameters differently. Little bit we will modify this circuit with respect to the primary winding. So the parameters of the secondary part, that is the resistance and the reactance, and the load of the secondary part is taken from the secondary to the primary network. This can be done considering that same power loss has to be there in whatever is there in the secondary winding, that is I2 square R2. This has to be equal to I1 square R2 dash. So we need to find what is the value of R2 dash that will give the same power loss when it was in the secondary part. So if in the secondary the power loss is I2 square R2, then what is the value of R2 dash which will give the same power loss, because in the primary network the current flowing is I1. So I1 square into R2 dash. So what is this R2 dash? That is referred from the secondary side to the primary side. So if we equate it, then we find that R2 dash is equal to I2 by I1 square into R2, and we know that I2 by I1 represent the values of the K, that is the transformation ratio. So we can say that R2 dash is equal to R2 by K square, and similarly the same reactance side is X2 dash is equal to X2 by K square. So here we have referred the resistance and the reactance from the secondary side to the primary winding. The load impedance is similar nature. We can say that ZL dash is equal to ZL by K square. So that is referred to the primary network. The current I2 dash and the voltage V2 dash are also referred from the secondary side to the primary side. So we know that I2 dash is equal to K time I2, and hence we can say that V2 dash is also equal to K times V2. So these are the referred quantities from the secondary side to the primary side. So we are dividing these quantities and find out what is the voltage and the current when the secondary quantities are referred to the primary side. And since all quantities are referred to the primary side, the transformer need not to be shown. So here we know that when we were having the transformer with primary network and the secondary network, and all the parameters from the secondary side we have referred to the primary network, then we can replace this transformer because the transformer is the ideal one which is having no losses. Now little bit changes we can do to make the calculation easier because the current I naught is very small. The no load component of the transformer current is basically 1 to 3% of the full load current, whether it is I1 or whether it is I2. So I0 is very small as compared to I1. Hence, when the drop due to the current I0 in the resistance and the reactance part, so here we have R1 and X1, and when the current I0 is flowing here, then this loss is very less. So the loss in the resistance of the primary network due to the no load current can be neglected because it is very less. So drop across R1 and X1 due to I0 can be neglected, and hence we can shift the no load component to the extreme left. So the shunt parameters is shifted to the extreme left of the network so that we can add the resistance and the reactance of the shifted parameters from the secondary side to the primary side. Now it is easy to add the parameter R1 and R2 dash because this represent the real part. So I can say that the resistance R01. So R01 is the resistance which is referred from the secondary side to the primary side plus whatever the resistance is already present in the primary side. So this is R1 plus R2 dash. R2 dash has been referred from the secondary side. So it is equal to R1 plus R2 by K square. Similarly, X01. So X01 is the summation of X1 plus X2 dash. So it is X1 plus X2 dash, which is equal to X1 plus X2 by K square. So this is the second equation. And hence the total impedance, we know that the impedance is equal to under root of R square plus X square. So here we can get the impedance is equal to under root of total resistance square plus total reactance square. Hence this entire network can be represented by one resistance, that is R01, and one reactance, that is X01, which makes the calculation easier. So from this network, we will be getting one more network with the modified form of one resistance and the reactance R01 and X01. Now the same thing if we do to refer on the secondary side instead of the primary side, then we need to find R02 and X02 component. So here the transformation ratio K square will be multiplied instead of divided. So the single resistance and single reactance we are getting on the secondary side with secondary parameter constant, and the primary parameter has been referred to the secondary side, and hence we can get the total impedance of the network as under root of R02 square plus X02 square. Also note that if we have already computed Z01, then we can refer that to the secondary side. Z02 is equal to K square into Z01. So the things to be remembered here is that shifting the primary parameter, whether it is resistance or reactance, to the secondary side, we have to multiply with K square. On the other hand, if we refer the secondary to the primary network, we have to divide by K square in the resistance and the reactance parameters. The next topic that we will take is the voltage regulation in a transformer. So when the transformer is loaded, as some electrical load can be put in the secondary of the transformer, then the secondary voltage V2 will fall, and these will result a drop across the resistance R2 and X2 because the current I2 will be flowing. So we have a resistance R2 and the reactance X2. Here the current I2 is flowing, and due to the load, when this transformer is loaded, this current will flow I2, and there will be a drop across this resistance and the reactance network. So the change in the voltage of the secondary from no load to full load condition, which is expressed in fraction of the no load secondary voltage, is called the regulation of the transformer. This can be represented by the fraction format, where we can say that the voltage regulation is the difference of the secondary terminal voltage under the condition from no load to the full load with the base value as taken as the no load value. So that is the change in the secondary terminal voltage. So these can be represented as E2 minus V2 by E2, because that is the no load voltage is E2 and the full load voltage is V2. If we want to express that in percentage, we have to multiply that with 100. So E2 minus V2 by E2 into 100 will give the voltage regulation. Now let us try to find what has happened, this voltage regulation in the actual transformer. So this is the phasor diagram that we have drawn for the transformer, considering it to be a lagging load. So the base or reference quantity, we have taken the secondary voltage, and the secondary current is lagging in nature by an angle phi. So the drop of the resistance, so in case we have the resistance R2, R02, so here we are talking about the total resistance R02 and the total reactance X02. And here whatever the current flowing is I2. So I2 R02 is the total resisting drop, and I2 X02 is the total reactive drop, which is at 90 degree with respect to I2 R02. Hence, in the secondary loop, the KVL equation we can write as E2 is equal to V2 plus the total drop in the transformer due to R02 and the total drop in the transformer due to X02. So here we can, this is all our vectors. So we have the vector representation. Here we have the J quantity which represent the 90 degree. Hence we will be getting the induced EMF E2 as a summation of V2 plus I2 R02 and I2 X02. So now if we need to calculate the total voltage drop, that is E2 minus V2, we have to resolve this phasor quantity. Let us see how to resolve it. So if we see what is E2, so E2 is the value of OC, this is E2, and the V2 is nothing but OA, so we can see that this is V2. Now OC can fall here in such a way that the total E2 representation can be in the form of OM. So OM is the equal to OC value, and OM can be written as OM can be written as here O. So when we subtract OM minus OA, we are getting value of AM. So this is what we are getting when we are subtracting OM minus OA. And this AM is equal to AN plus NM. From here we will be adding AN plus NM. Easily we can see that this value is very less. So we can neglect the value of NM, which is very small, and we can take the value of AN. Again, this AN can be further splitted up into AD plus DN. So AD plus DN, and DN is equal to BL. So I can say that AD plus BL is the total voltage drop. Now if we see what is this AD and what is the value of BL, this is what the voltage drop represent. So AD is nothing but I2 R02 cos phi, and BL is nothing but I2 X02 sin phi. And voltage regulation hence can be written as the total voltage drop, which is I2 R02 cos phi plus I2 X02 sin phi divided by E2 into 100. So this derivation whatever we have done is considering that the load is lagging in nature. So if the load is leading in nature, the approximate voltage drop, where we will be having a negative sign here, so I2 R02 cos phi minus I2 X02 sin phi, and percentage regulation can be written by this formula. In general, we can write the percentage regulation formula with the plus minus in between, where plus indicate the lagging power factor and minus indicate the leading power factor. The same derivation can be done from the primary side, because this derivation has been done from the secondary side. So if we are doing this derivation from the primary side, all the current and the other parameters will be taken from the primary side. So we will be having I1 R01 cos phi plus minus I1 X01 sin phi, and here in the denominator we have V1, which is the primary voltage. Now, if we find the regulation with little bit mathematical manipulation, where we have this 100, if we take it inside, then we can say that 100 I2 R02 divided by E2 cos phi plus minus 100 I2 X02 by E2 sin phi. If we observe this quantity carefully, we can say that the percentage resistive drop and percentage reactive drop can be represented by VR and Vx, where the VR value is I2R02 by E2 into 100, that is in percentage, and Vx is I2X02 by E2 into 100, that is percentage reactive drop. So voltage regulation can be determined directly from the voltage drop, or if it is mentioned that what is the resistive drop and the reactive drop in the problem, we can take it in by this formula. The next topic is to determine the efficiency of the transformer. We know that efficiency is defined as the ratio of the output power by input power of any device, not only a transformer. Here, if the input power is written in terms of the output power plus losses, then we have the new formula for efficiency as output power by output power plus losses. We know that the losses in the transformer is the sum of iron losses plus the copper losses. So we can further calculate the efficiency in this formula. Yes. Now here the output power can be written as V2 I2 cos phi 2. This is what is there from the secondary side, and here the iron losses can be written as Pi and the copper losses can be written as Pc. And again the V2 I2 cos phi 2 is the output power. So this formula can be used to find the efficiency of the transformer, where the V2 and I2 are the secondary terminal voltage and the full load secondary current. So we can note down here that I2 represent the full load current. Power factor of the load is cos phi 2, and Pi and Pc represent the iron loss and the copper loss. Iron loss is the summation of hysteresis loss plus eddy current loss. The copper loss full load is equal to I square into total resistance of the entire transformer. So when we say the copper loss, this is the full load copper loss, which is equal to, we can calculate as I1 square into R01, or we can say this one is equal to I2 square R02, or separately if we are calculating, then we can say this is equal to I1 square R1 plus I2 square R2. So these all will give the same copper loss under the full load condition. Now if the transformer is loaded as X fraction of the full load, then efficiency formula will change. So output power, which is the full load output power, that will be multiplied with X here to indicate the output power at a particular fraction of the full load. Iron loss, we know it is a constant quantity, and copper loss is a variable quantity which is changing as X square into full load copper loss. So this formula can be represented again X into V2 I2 cos phi 2. Iron loss is a constant loss, and X square into total copper loss is given by I2 square into total resistance of the network, either from the primary side or from the secondary side. What is the condition for the maximum efficiency? So if we plot the efficiency with respect to the loading, we will be getting the curve like this. So this is the efficiency curve. Now efficiency will be maximum. So we have this efficiency will be maximum corresponding to a particular load. So what is that condition when the efficiency is maximum? Let us see. So efficiency formula is given by this one, where we have the output power by output power plus losses. And since in the secondary where the load is connected, the current I2 is flowing, and this I2 is changing with respect to the load. So when the load is changing, the I2 will be changing. So if we divide the numerator and the denominator with I2, then we will get the equation. Now note here that the voltage V2 is constant for a particular transformer depending upon the devices that we connected, and for a given power factor cos phi 2, eta, that is the efficiency, will depend only on the secondary current. So if we differentiate the efficiency equation with respect to the current I2 and equate with 0, we are going to get the relationship like this. So we get the iron loss is equal to I2 square R2. It means that iron loss is equal to copper loss of the transformer when the efficiency is maximum. So iron loss is a constant loss and copper loss is a variable loss. So when the current is flowing in the transformer at the current, when the copper loss become equal to iron loss, then the efficiency will be maximum. Now, what is that current which is giving the maximum efficiency? So the current is equal to under root of iron loss by RT, because we have seen that the iron loss is equal to I2 square into RT. So from here we can find what is the current I2. So if X is the fraction of the full load kVA at which the efficiency is there, then iron loss remains constant and copper loss is equal to X square into PC. So for the maximum efficiency, we can say that iron loss is equal to copper loss and copper loss is equal to X square PC for a particular load. Then that particular load X fraction is given by under root of iron loss by copper loss. What is the output kVA corresponding to maximum efficiency then? Now kVA full load multiplied with the fraction of the load at which the transformer is operating will give you the efficiency maximum. It means efficiency maximum, we can say that kVA full load multiplied with the value of X, which we are getting in the previous equation as under root of iron loss by copper loss. Now, the next topic will take the open circuit and short circuit test on the transformer. So, why we are calculating this open circuit and short circuit test? So, the open circuit test purpose is to determine the iron loss or the core loss, which is given by Wi. This is the first reason. The second reason is to compute the magnetizing resistance denoted by R0 and the magnetizing reactance denoted by X0. So if we see the shunt parameters, so in the shunt parameters we have the value of this is R0, this is X0, and here the current I0 is flowing, and this one is basically IW and this current is basically I mu. So the supply voltage we are giving here, that is V1. So all the shunt parameters are related with the open circuit test of the transformer and the power that we are measuring. So if we connect one wattmeter here, the power which is reflecting in the wattmeter will represent the iron or the core losses. So let us see the test connection. So here when we say that the transformer, if it is in the form of low voltage by high voltage or high voltage by low voltage, this may be the two possibilities of the connection. We keep the high voltage side open. So if this is open on, then this side will be the high voltage side. And all meters we will be connecting on the low voltage side. So low voltage side, the meters will be connected whether it is ammeter, voltmeter or wattmeter. Now this ammeter, which is indicating the no load current I0, which is 3 to 5% of the full load current or very less than that. The copper loss is negligible and the wattmeter indicates only the iron loss. So this W represent only the iron loss in the transformer. So if it is so, then these are the readings that we are obtaining after doing the experiment: wattmeter reading, the voltmeter reading and the no load current I0. So we know that the iron loss will be given by Wi is equal to V1 I0 cos phi naught. Hence, first we will determine what is the power factor. So power factor will be equal to, from this equation, first equation, Wi by V1 I0. Hence, we can find out IW and I mu from the phasor diagram. We have discussed this in the first lecture. So when we have IW, I0, the no load component of the current, so this will be equal to phi naught. And these current on the x-axis we will be having I mu, and on the y-axis whatever the current we will be having IW. And this is the phi axis, flux axis, and this is the voltage V1 axis. So I can see here that IW is nothing but I0 cos phi naught and I mu is equal to I0 sin phi naught. So we have the second equation and the third equation. Now since the shunt parameters, if we draw, this is R0 and X0. So here we have R0 and here X0, and we have already calculated what is the current flowing here, that is IW and I mu, and this is in parallel with the supply voltage V1. So it means R0 and X0 we can calculate from the Ohm's law as the voltage divided by the current which is flowing in the individual parameters. So this can be your fourth formula and this can be fifth formula. So we can obtain the shunt parameters of the transformer equivalent circuit using the open circuit test. Now we'll do the short circuit test. So short circuit test purpose is to determine the full load copper loss first and the equivalent resistance and the equivalent reactance, whether it is from the primary network or whether it is from the secondary network. So it will represent the series parameter. So if we can see that draw the equivalent circuit, we will have one resistance and one reactance. So this is, if we are taking R01, this is X01, total resistance and the total reactance. So these represent the full load copper losses. So here you have the copper loss. So the test connection, if we see, we have to sort, because this is a short circuit test, we have to sort the low voltage side. We never short circuit the high voltage side, and low voltage is applied to the other winding. So this side we will be having the high voltage winding, and the voltage is slowly applied until the full load current flows in the winding. So this ammeter should show the full load current. So this ammeter should show the full load current, and slowly the voltage has to be varied. Normally the applied voltage is 5 to 10% of the rated voltage. And then in the short circuit test, the flux is produced in the core is very small and iron losses are very small. So we can neglect the iron loss because it is zero, and the total loss which is shown in the wattmeter is basically the copper losses. So the reading that we have obtained is the wattmeter reading, the voltmeter reading and the ammeter reading. And here SC indicate that short circuit test has been done on the transformer. So first we will find what is the impedance, total impedance of the network, which is voltage short circuit by current short circuit. Then we can find what is the resistance short circuit, which is power W short circuit divided by current I square, because we know that the short circuit power is equal to ISC square multiplied with RSC. So we can find what is this RSC. Third, we can find the reactance XSC is under root of ZSC whole square minus RSC whole square. So these will give me the series parameters of the equivalent circuit of the transformer. So open circuit test and short circuit test usually give the shunt and the series parameters, which are representation of iron loss and the copper loss in a transformer. So all the parts of a transformer is over. All the three parts together complete the fundamentals of the transformer from the first year BTech point of view. Thank you for now. See you in the next lecture.